Tonight, we're going to explore something that seems impossible, but is absolutely true. Everything you've ever touched, every object you've ever held, every surface you've ever walked on is almost entirely nothing. Empty space. The chair you're sitting in right now, the phone or computer you're using, even your own body, all of it is more than 99% emptiness. This isn't some mystical claim or philosophical metaphor. This is physics. Hard, measurable, proven science. And here's what makes it even stranger. That emptiness isn't really empty. It's seething with invisible activity that shapes everything in the universe. By the end of this journey, you're going to understand why nothing is actually everywhere, and why that might be the most important fact about reality you've ever learned. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe would really help the channel grow. It's a small gesture, but it makes a meaningful difference for me. Now, let's begin. Let's start with something you do every day without thinking about it. You pick up a cup of coffee. You feel its weight in your hand. You feel the warmth of the ceramic against your palm. You feel the solid surface pressing against your fingers. Everything about this experience tells you the cup is solid. It has mass. It has substance. It occupies space in a way that seems completely filled with matter. Your brain processes this information instantly. Solid object, real thing, something is there. This is how we navigate the world. We trust our senses. We rely on touch to tell us what's real and what isn't. A rock is solid. Water is liquid. Air is invisible but present. These categories seem obvious, fundamental, beyond question. But here's what's actually happening at the atomic level. That cup, like everything else in the universe, is made of atoms. Atoms are the building blocks of all matter. Everything you've ever seen, touched, or experienced is made of atoms. The air you're breathing right now contains about 25 sextillion atoms per liter. That's a 25 followed by 21 zeros. Atoms are everywhere, making up everything. For a long time, humans thought atoms were the smallest possible unit of matter. The word atom comes from the ancient Greek word atomos, meaning indivisible. The philosophers Leucippus and Democritus proposed around 450 years before the Common Era that if you kept cutting matter into smaller and smaller pieces, you would eventually reach a point where it couldn't be divided anymore. These ultimate building blocks, they argued, were the fundamental units of reality. They were right about the basic concept. Matter is made of discrete particles, but they were wrong about atoms being indivisible. In the late 19th and early 20th centuries, scientists discovered that atoms have internal structure. They're made of smaller parts, and understanding those parts reveals something astonishing about the nature of matter. Here's the strange part. Atoms themselves are almost entirely empty space. Let me explain what an atom actually looks like. At the center of every atom is a nucleus. This nucleus is incredibly small, containing protons and neutrons packed tightly together. Protons carry a positive electrical charge. Neutrons carry no charge at all. Together, they form a dense core at the heart of the atom. Orbiting around this nucleus, at relatively vast distances, are electrons. Electrons are negatively charged particles, much lighter than protons or neutrons. They don't orbit in neat circles like planets around a sun. Instead, they exist in probability clouds, smeared out regions of space where they're likely to be found at any given moment. But for our purposes, what matters is that electrons are far from the nucleus, separated by what, at the atomic scale, is an enormous gulf. Now, here's where things get mind-bending. The nucleus of an atom is about 100,000 times smaller than the atom itself. Let me say that again because it's crucial to understanding what I'm about to tell you. The nucleus, which contains almost all of the atom's mass, is 100,000 times smaller than the atom as a whole. 100,000 times. That's not a small difference. That's not even a large difference. That's an almost incomprehensible difference in scale. To visualize this, imagine you took a hydrogen atom, the simplest atom, with just one proton and one electron, and scaled it up so that the nucleus was the size of a marble, about 1 centimeter in diameter. At this scale, where would the electron be? The electron orbiting around that marble-sized nucleus would be found somewhere in a sphere about 1 kilometer away. That's more than half a mile. The entire space between the marble-sized nucleus and that distant electron would be empty. Nothing there. Just space. Think about that. If the nucleus were a marble sitting on the 50-yard line of a football stadium, the electron wouldn't be in the stands. It wouldn't be in the parking lot. It would be somewhere in the next town over. And everything in between, the entire stadium, the surrounding streets, the neighboring buildings, all of that space would be empty. Now think about what this means for the objects around you. That coffee cup, that chair, the floor beneath your feet, your own hand. And those atoms are almost entirely empty space with tiny dense nuclei surrounded by electrons at relatively enormous distances. If you could somehow remove all the empty space from the atoms in your body and pack the nuclear material together, you would shrink down to a size smaller than a grain of sand. All the matter that makes up you, every cell, every organ, every bone and muscle and nerve fiber, every thought and memory contained in your brain, it would all fit into something smaller than you could see with the naked eye. The rest, the overwhelming majority of what we call your body, is nothing but empty space. This isn't an approximation or an exaggeration. Calculations show that atoms are more than 99.99999999999% empty space. The actual matter, the protons, neutrons, and electrons, makes up less than a trillionth of the volume of an atom. The emptiness isn't slight, it's total. It's overwhelming. It's the fundamental nature of what we call solid matter. You are mostly nothing. I am mostly nothing. The chair you're sitting on, the device you're using to read or listen to this, the walls around you, all of it is mostly nothing. The entire visible universe, all the stars and planets and galaxies that seem so substantial, it's almost entirely void with tiny specks of actual matter scattered throughout like dust motes in an empty warehouse. So why does the coffee cup feel solid? Why can't your hand pass right through the table? If everything is mostly empty space, why doesn't everything just fall through everything else? This is an excellent question, and the answer lies in the fundamental forces of nature, specifically electromagnetism and something called the Pauli exclusion principle. When you press your hand against a table, the atoms in your hand are not actually touching the atoms in the table. What you feel as solidity is actually electromagnetic repulsion. The electrons in the atoms of your hand are negatively charged. The electrons in the atoms of the table are also negatively charged. And here's one of the most basic rules of electricity. Like charges repel each other. As the electron clouds of your hand's atoms approach the electron clouds of the table's atoms, they push against each other. The closer they get, the stronger the repulsion becomes. This electromagnetic force increases rapidly as the distance decreases. By the time the electron clouds are close enough for you to perceive contact, the repulsive force is enormous. It pushes back against your hand with tremendous strength. This electromagnetic repulsion is what creates the sensation of solidity. You feel the table pushing back against your hand. Your brain interprets this as touching a solid surface, but the atoms never actually made contact. They were pushing against each other from a distance, repelled by the fundamental electromagnetic force. Here's a strange and somewhat unsettling implication of this. you have never actually touched anything in your entire life. Every time you thought you were touching something, you were feeling the electromagnetic force pushing back against you. The atoms in your hand and the atoms in whatever you thought you were touching never made contact. They were repelling each other across what, at the atomic scale, is a significant distance. When you hold hands with someone you love, your atoms and their atoms never touch. When you pet your dog or hug your child, no actual contact occurs. The warmth you feel, the pressure, the sense of connection, all of it is electromagnetic repulsion translated by your nerves into the sensation of touch. This isn't sad or diminishing. The electromagnetic force is just as real as physical contact would be if it existed. The sensation is genuine, the experience is authentic. But the mechanism is different from what we intuitively imagine. We're not pressing matter against matter, we're pressing force fields against force fields. The Pauli exclusion principle adds another layer to this illusion of solidity. This principle, discovered by physicist Wolfgang Pauli in 1925, states that no two electrons can occupy the same quantum state in the same location. Electrons have properties like spin and energy level. The Pauli exclusion principle says that two electrons in the same place can't have all the same properties. When the electron clouds of different atoms get too close, this principle prevents them from overlapping completely. The electrons essentially refuse to share the same space. This creates additional resistance beyond what electromagnetic repulsion alone would provide. It's why matter is as rigid as it is, why solids hold their shape instead of mushing together like soft clay. Together, electromagnetic repulsion and the Pauli exclusion principle create what we experience as solid matter. But it's really an illusion in the technical sense. It's a force field created by electromagnetic repulsion and quantum mechanical rules. The actual matter involved is vanishingly small. The rest is empty space. Let me give you some more comparisons to help you truly grasp this scale. If the nucleus of a hydrogen atom were the size of a basketball sitting at center court in a basketball arena, the electron would be somewhere in the parking lot outside the stadium, maybe farther. The entire arena, all the seats, all the corridors, all the concession stands, would be empty. The basketball at center court would be the only thing with any substance. Everything else would be void. If you scaled up a single atom to the size of a great cathedral, say Notre Dame in Paris before the fire, with its vast interior stretching hundreds of feet in every direction, the nucleus would be about the size of a fly buzzing around inside. One small fly in the middle of that enormous space. The rest of that vast interior would be nothing. Consider the sun for a moment. The sun is enormous, about 864,000 miles in diameter. You could fit more than 1 million Earths inside it. The sun dominates our cosmic neighborhood, a massive ball of hydrogen and helium undergoing constant nuclear fusion at its core. And yet, if you removed all the empty space from the atoms in the sun and compressed the actual matter together, the remaining material would form a sphere only about 6 miles across. That's roughly the distance you might drive to get to work. You could walk across the compressed sun in a couple of hours. All the matter in the sun, which seems so vast and powerful, would fit in something smaller than a medium-sized city. The same is true for Earth. Our entire planet, with its mountains reaching 5.5 miles into the sky, its oceans plunging 7 miles deep, its mass of nearly 6 trillion kilograms, if you removed all the empty space from its atoms, would compress down to something about the size of a large marble. All the mountains, all the oceans, all the continents, every living thing that has ever existed on Earth, all the dinosaurs and trees and bacteria and humans, all of it would fit into something you could hold between your thumb and forefinger. You could lose the compressed Earth in your pocket. And yet, we walk around every day completely unaware of this. We experience the world as solid, substantial, filled with matter. We build houses and bridges and skyscrapers that feel permanent and heavy. We trust that the ground will hold us up. that walls will keep things out, that objects have real presence in the world. All of this is true in a practical sense. The forces that create the illusion of solidity are very real. Electromagnetic repulsion doesn't care that atoms are mostly empty space. It still pushes back with enormous strength. You can't walk through walls just because you know they're mostly empty. The physics that makes walls solid is just as real as the physics that makes atoms empty. But there's something profound about understanding the true nature of matter. It changes how you see the world. Every time you pick up an object, you can remember that you're holding mostly nothing. Every time you look at another person, you can remember that they're more than 99% empty space. Every time you look in the mirror, you can remember that the face staring back at you is almost entirely void. Let me take you deeper into atomic structure, because understanding exactly how empty atoms are requires understanding what the nucleus actually is. The rabbit hole goes deeper than you might expect. The nucleus contains protons and neutrons. These particles are much more massive than electrons. A proton has about 1,836 times the mass of an electron. A neutron is slightly heavier still. So even though electrons occupy most of the volume of an atom, spread out in their probability clouds far from the nucleus, they contribute almost nothing to its mass. The nucleus, tiny as it is, contains more than 99.9% of an atom's total mass. For decades, physicists thought protons and neutrons were fundamental particles, indivisible units like atoms were once thought to be. But in the 1960s and 70s, experiments at particle accelerators revealed that protons and neutrons have internal structure. They're made of smaller particles called quarks. Each proton contains 3 quarks, 2 up quarks and 1 down quark. Each neutron also contains 3 quarks, 1 up quark and 2 down quarks. These quarks are bound together by particles called gluons, which carry the strong nuclear force. The strong force is one of the 4 fundamental forces of nature, and it's aptly named. It's the strongest force we know of, powerful enough to hold quarks together against the electromagnetic repulsion that would otherwise push them apart. Here's something fascinating that makes the story even stranger. The quarks inside a proton or neutron account for only about 1% of the proton or neutron's mass. Just 1%. So where does the other 99% come from? The answer is energy. Specifically, the energy of the gluons binding the quarks together. According to Einstein's famous equation E equals mc squared, energy and mass are equivalent. They're 2 forms of the same thing. The binding energy of the strong force, the energy stored in the gluon field holding the quarks together, manifests as mass. So even the solid-seeming nucleus, the dense core of the atom where almost all the mass resides, is mostly energy rather than matter in any traditional sense. The quarks themselves are point-like particles with no measurable size. As far as our most precise experiments can tell, quarks have 0 volume. They're mathematical points, occupying no space at all. The mass we detect comes from energy, from the forces binding these dimensionless points together. This means that when we ask what matter really is, the answer becomes increasingly strange. At the deepest level, particles have no size. They're excitations in quantum fields, ripples in abstract mathematical structures that permeate all of space. The solidity we experience in everyday life is built on foundations that, when examined closely, seem almost ghost-like. The chair you're sitting on is made of atoms, which are mostly empty space, which contain nuclei made of quarks and gluons, where the mass comes from energy, and the quarks themselves are points without volume. It's emptiness all the way down. Let me tell you about an experiment that proved this beautifully and changed physics forever. In 1911, physicist Ernest Rutherford conducted what became known as the gold foil experiment. He was working at the University of Manchester with his colleagues Hans Geiger and Ernest Marsden. They wanted to understand the structure of the atom. At the time, The prevailing model of the atom was called the plum pudding model, proposed by J. J. Thomson, who had discovered the electron in 1897. In this model, atoms were thought to be solid spheres of positive charge with electrons embedded throughout, like raisins scattered through a pudding. The positive charge was spread evenly, filling the entire volume of the atom. This seemed reasonable based on the evidence available at the time. Rutherford's team fired alpha particles at a thin sheet of gold foil. Alpha particles are helium nuclei, consisting of 2 protons and 2 neutrons. They're positively charged and relatively massive. According to the plum pudding model, alpha particles should pass through the gold foil with only slight deflection. The positive charge was spread out, so there shouldn't be anything concentrated enough to cause a major deflection. What they found shocked everyone. While most alpha particles did pass straight through the foil, as expected, a small fraction were deflected at large angles, and some, about 1 in 8,000, bounced almost straight back toward the source. Rutherford was astonished. He later described his reaction in a famous quote. He said it was almost as incredible as if you fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. Artillery shells don't bounce off tissue paper. Something unexpected was happening. The only possible explanation was that the positive charge of the atom and most of its mass was concentrated in a tiny central nucleus. Most of the alpha particles passed through the empty space of the atoms without encountering anything. They sailed through like bullets through fog. Only those few that happened to come close to a nucleus were deflected by the concentrated positive charge, and those that hit a nucleus almost head-on bounced straight back. This experiment proved that atoms are mostly empty space. The gold foil, which seemed solid, was actually more like a collection of tiny points separated by vast emptiness. The alpha particles sailing through were passing through nothing at all, missing the nuclei entirely because the nuclei were so small compared to the total volume of the atoms. Every solid object you've ever encountered is like that gold foil. It seems substantial, but it's mostly gaps. The forces between atoms create the sensation of solidity, but the atoms themselves are almost entirely void. You could fire microscopic bullets through solid steel, and most of them would pass through without hitting anything, because most of the steel, like most of everything, is empty space. There's another way to appreciate the emptiness of matter. Consider what happens when matter is compressed to its maximum possible density. This occurs in neutron stars, the collapsed remnants of massive stars that have exploded as supernovae. When a large star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses catastrophically. In a neutron star, the gravitational force is so strong that it overcomes the electromagnetic repulsion between electrons. The electrons are squeezed into the protons, combining to form neutrons. What remains is a ball of neutrons packed as tightly as they can be, essentially touching each other. A neutron star might contain 1.5 times the mass of our Sun compressed into a sphere only about 12 miles across. Think about that. The mass of the Sun, which is 864,000 miles in diameter, compressed into something the size of a city. A teaspoon of neutron star material would weigh about 6 billion tons. If you could somehow bring a teaspoon of neutron star matter to Earth, it would weigh more than Mount Everest. This is matter with most of the empty space removed. This is what atoms look like when you squeeze out the void. The fact that you can compress more than a sun's worth of matter into something 12 miles across tells you how empty normal matter is. The Sun is 864,000 miles in diameter. A neutron star with similar mass is about 12 miles across. That's a compression factor of about 70,000 in diameter, which corresponds to a compression in volume of more than 300 trillion. Normal matter is that empty. You could squeeze it down by a factor of hundreds of trillions before the particles themselves start touching. And even neutron stars aren't compressed to the absolute limit. If you added more mass to a neutron star, eventually even the strong nuclear force holding neutrons together would fail. The star would collapse further, becoming a black hole. At that point, all the matter would be compressed into a singularity, a point of theoretically zero volume and infinite density. Though physicists suspect that quantum effects prevent true singularities from forming, we don't yet have a complete theory of what happens inside black holes. The mathematics breaks down, the physics becomes uncertain. The progression from normal matter to neutron stars to black holes illustrates the vast emptiness hidden in everyday objects. The matter around you, if compressed to neutron star density, would shrink to a tiny fraction of its current size. If compressed further to black hole density, it would effectively disappear, becoming a point in space. The air around you right now, the air you're breathing, is also mostly empty space. Air is made of molecules, primarily nitrogen and oxygen, with smaller amounts of argon, carbon dioxide, and other gases. These molecules are in constant motion, bouncing off each other and off the walls of whatever container holds them. At room temperature, air molecules move at speeds of several hundred meters per second, colliding billions of times every second. But even the air is mostly nothing. The molecules in air are widely spaced compared to their size. There are about 25 quintillion molecules of nitrogen and oxygen in every cubic centimeter of air at sea level. That sounds like an enormous number, and it is, but those molecules are still separated by distances many times their own diameter. The space between air molecules is vastly larger than the molecules themselves. The air you breathe is almost as empty as the atoms it's made of. Between individual air molecules, there's nothing, just vacuum. The molecules bounce around, colliding occasionally, but most of the time they're traveling through emptiness. A nitrogen molecule might travel hundreds of nanometers between collisions. At the molecular scale, that's a long journey through void. Even in the densest materials, in metals and rocks and the cores of planets, atoms are separated by gaps. There's always space between them. There's always nothing mixed in with the something. The densest naturally occurring element, osmium, packs its atoms more tightly than any other substance on Earth. But even osmium is mostly empty space. The atoms are closer together, but the atoms themselves are still more than 99% void. This emptiness at the atomic scale is just the beginning of our exploration, because when we zoom out from atoms to larger structures, when we start looking at the space between objects instead of within them, we find even more nothing. Much, much more. The space between you and the nearest wall is filled with air, but that air is mostly empty, as we've discussed. Between Earth and the Moon, there's even less. Space is often described as a vacuum, and while it's not a perfect vacuum, it's astonishingly close. The space between Earth and the Moon contains only a few atoms per cubic centimeter. Compare that to the quintillions of molecules in the same volume of air at sea level. Outer space is almost perfectly empty, a void so complete that it defies everyday intuition. And when we look beyond the Moon, beyond our solar system, beyond our galaxy, we find emptiness on scales that dwarf anything we've discussed so far. The voids between stars and galaxies are so empty, so vast, that the emptiness inside atoms seems crowded by comparison. The atomic void is just a preview, a gentle introduction to the true emptiness that fills the cosmos. In the next section, we'll explore these cosmic voids. We'll see just how empty the universe really is. We'll travel from the space between planets to the gulfs between stars to the enormous voids between galaxy clusters. And we'll discover that the nothing between worlds is far more vast than the something that makes up those worlds. The emptiness within atoms is profound, but it's nothing compared to the emptiness between them, the emptiness that stretches across light years and fills most of the observable universe. We've seen that atoms are mostly empty space. The very substance that makes up everything you've ever touched is more than 99% nothing. But now, let's zoom out, way out. Because the emptiness inside atoms is just a preview, a gentle introduction to the emptiness that exists at every scale of the universe. If the void within atoms surprised you, what comes next will astonish you. The cosmos is empty on scales that make atomic emptiness seem almost crowded. We're about to journey from the space between planets to the gulfs between stars to the vast cosmic voids between galaxy clusters. And at every step, we'll find more nothing than something. Let's start close to home. Our solar system seems full of stuff when you look at a diagram. You see the sun in the center, 8 planets orbiting around it, dozens of moons, rings around Saturn, asteroid belts, comets streaking past. It looks crowded, like a busy intersection with traffic flowing in all directions. These diagrams give the impression that space is packed with objects, but those diagrams are deceptive. They have to be, because if they were drawn to scale, you wouldn't be able to see anything. The solar system is almost entirely empty space. The sun dominates our cosmic neighborhood. It contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, accounts for less than 0.2%. The sun has a diameter of about 864,000 miles. That sounds enormous, and it is. You could fit about 1,300,000 Earths inside the sun. It's a massive ball of hydrogen and helium, fusing atoms in its core and radiating energy in all directions. But the solar system extends far beyond the sun. Neptune, the outermost planet, orbits at an average distance of about 2,800,000,000 miles from the sun. That's 30 times farther from the sun than Earth is. Earth orbits at about 93 million miles from the sun. Neptune orbits at nearly 3 billion miles. The space between these orbits is almost entirely empty. Let me give you a sense of this scale. If you shrunk the sun down to the size of a basketball, about 9.5 inches in diameter, and placed it at one end of a football field, where would the planets be? Mercury, the innermost planet, would be a tiny speck, smaller than a grain of sand, about 33 feet from the basketball. Venus would be a slightly larger speck, about 62 feet away. Earth would be another tiny grain of sand, about 85 feet from the basketball sun. Mars would be a slightly smaller speck, about 130 feet away. Then comes a huge gap. The asteroid belt, that band of rocky debris between Mars and Jupiter, would span from about 170 feet to about 290 feet from the basketball. But remember, the asteroid belt isn't a dense field of rocks like you see in movies. It's mostly empty space with occasional rocks scattered through it. If you flew through the asteroid belt, you'd be unlikely to see a single asteroid without specifically looking for one. Jupiter, the largest planet, would be a marble about 1 inch in diameter, sitting about 440 feet from the basketball. Saturn, with its famous rings, would be a slightly smaller marble about 800 feet away. That's nearly 3 football fields from the sun. Uranus would be a pea about 1,600 feet away, almost a third of a mile. And Neptune would be another pea about half a mile from the basketball sun. Half a mile. A 10 to 15 minute walk from the basketball to reach the outermost planet. And what's between all these objects? Nothing. Almost perfectly nothing. The space between planets is a near-perfect vacuum. There are a few atoms per cubic centimeter, mostly hydrogen and helium particles streaming out from the sun as the solar wind. But compared to the density of air at sea level, interplanetary space is essentially void. Let me put some numbers on this comparison. Air at sea level contains about 25 quintillion molecules per cubic centimeter. That's a 25 followed by 18 zeros. Every cubic centimeter of air you breathe is packed with an almost unimaginable number of molecules bouncing around, colliding with each other billions of times per second. The space between planets contains maybe 5 to 10 particles per cubic centimeter. That's it. Single digits. The difference between air and interplanetary space is about 18 orders of magnitude. That means interplanetary space is about a quintillion times emptier than the air in your lungs. If you could somehow collect all the atoms in a cubic mile of interplanetary space, you might have enough to make a small grain of dust. A single cubic mile of this near-perfect vacuum contains almost nothing. The Voyager 1 spacecraft, launched in 1977, has been traveling away from Earth for nearly 50 years. It's now about 15 billion miles from the Sun, far beyond Neptune, beyond Pluto, pushing into the space between our solar system and the stars. It's traveling at about 38,000 miles per hour. That's fast. At that speed, you could travel from New York to Los Angeles in less than 4 minutes. You could circle Earth in about 40 minutes. And yet, after nearly 5 decades of constant travel at this tremendous speed, Voyager has barely scratched the surface of the emptiness surrounding our solar system. It's still closer to the Sun than to any other star. It's still within the Sun's gravitational influence. The void extends much, much farther. The solar system doesn't end at Neptune. Beyond the planets lies the Kuiper Belt, a region of icy bodies extending from Neptune's orbit to about 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the Kuiper Belt extends to about 4,650,000,000 miles from the Sun. The Kuiper Belt contains thousands of known objects, and probably millions more that are too small and faint to detect. Pluto lives here, along with other dwarf planets like Eris, Makemake, and Haumea. But even the Kuiper Belt is mostly empty. The objects are spread so far apart that you could travel through the entire region and never come close to any of them. But even the Kuiper Belt isn't the edge. Far beyond it lies the Oort cloud, a vast spherical shell of icy objects that surrounds the entire solar system like a cosmic bubble. The Oort cloud is thought to extend from about 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. At its outer edge, the Oort cloud is nearly 2 light-years from the Sun. That's about 12 trillion miles. No spacecraft has ever visited the Oort cloud. No telescope has ever directly imaged an object there. We know it exists because long-period comets that take thousands or millions of years to orbit the Sun, must come from somewhere. They fall inward from the outer reaches of the solar system, loop around the Sun, and head back out into the darkness. Their orbits trace back to a vast, distant shell of icy bodies at the edge of the Sun's influence. The Oort cloud might contain trillions of icy objects, leftover debris from the solar system's formation 4.5 billion years ago. But these objects are spread across a volume so vast that the chance of any 2 objects coming close to each other is vanishingly small. The Oort cloud is almost entirely empty. If you were somehow transported to the middle of the Oort cloud, what would you see? Darkness. Nothing but darkness in every direction. The Sun would appear as just another star, bright but not dominant. Certainly not the blazing disk you see from Earth. The nearest Oort cloud object might be billions of miles away, far too distant to see. You would float in emptiness, surrounded by 12 trillion miles of essentially nothing, with the faint glow of distant stars your only companions. Now, let's leave the solar system entirely and venture into the space between stars. This is where distances become so large that our usual measurements stop making sense. This is where emptiness reaches scales that challenge human comprehension. The nearest star to our Sun is Proxima Centauri, part of a triple star system called Alpha Centauri. It's about 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at about 186,000 miles per second. Light is the fastest thing in the universe. Nothing can travel faster, and even light takes more than 4 years to cross the gap between our Sun and the nearest star. Let's calculate what this means in miles. Light travels at about 186,000 miles per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and about 365 days in a year. Multiply all of that together, and you get about 5.88 trillion miles per light year. So Proxima Centauri, at 4.24 light years, is about 25 trillion miles away. 25 trillion. That's a 25 followed by 12 zeros. To help grasp this distance, let's return to our scaled model, where the Sun is a basketball. In this model, Earth is a grain of sand 85 feet away, and Neptune is a pea about half a mile away. The Oort cloud extends to perhaps 2 miles from the basketball. Where is Proxima Centauri in this model? At this scale, Proxima Centauri would be another basketball about 4,300 miles away. That's roughly the distance from New York to London, or from Los Angeles to Tokyo, if you went the short way across the Pacific. Think about that for a moment. Let it sink in. If our entire solar system, from the Sun out to the Oort cloud, fits within a couple of miles, the nearest star is 4,000 miles away, and everything in between. Every single mile of that 4,000-mile journey is empty. Not just mostly empty. There's almost nothing there. A few atoms of hydrogen drifting through every cubic centimeter of space. That's it. Interstellar space, the region between stars, is one of the emptiest environments in the universe. The density of matter in interstellar space averages about 1 atom per cubic centimeter. 1 atom. In a cubic centimeter. Compare that to the quintillions of molecules in every cubic centimeter of air at sea level. Interstellar space is emptier than air by a factor of more than 10 trillion. What would it be like to travel through this void? At Voyager's current speed of 38,000 miles per hour, it would take about 73,000 years to reach Proxima Centauri. 73,000 years. Human civilization is only about 10,000 years old. You could run through the entire history of human civilization 7 times over and still not have traveled from our Sun to the nearest star. And Voyager isn't even headed toward Proxima Centauri. It's traveling in a different direction, toward a star called AC plus 79 degrees 3888, which it will pass at a distance of about 1.7 light years in about 40,000 years. Pass, not arrive at. Voyager will never actually reach any star. It will drift through interstellar space, essentially forever. A tiny message in a bottle lost in an infinite ocean. The fastest spacecraft ever launched, the Parker Solar Probe, can reach speeds of about 430,000 miles per hour when it's close to the Sun, using the Sun's gravity to accelerate to tremendous velocities. Even at that speed, more than 10 times faster than Voyager, it would take about 6,500 years to reach Proxima Centauri. Interstellar travel, the kind you see in science fiction movies where spacecraft zip between stars in days or weeks, is essentially impossible with any technology we can currently imagine. The distances are simply too vast. The emptiness is too complete. Let's zoom out further. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Our best estimates put the number at around 200 to 400 billion. That sounds like a lot. It sounds crowded. Surely a galaxy with hundreds of billions of stars must be full of stuff. But remember the distances involved. We just established that the nearest star to our Sun is more than 4 light years away. That's typical for stars in our region of the galaxy. The average distance between stars in our neighborhood is about 5 light years. That's about 30 trillion miles of emptiness between each pair of neighboring stars. The Milky Way is about 100,000 light years across. If you could somehow travel at the speed of light, the maximum speed allowed by the laws of physics, it would take you 100,000 years to cross from one side of the galaxy to the other. 100,000 years of traveling at 186,000 miles per second, and most of what you'd be traveling through would be nothing. Empty space with occasional stars scattered throughout like grains of sand on a beach miles wide. Let me try another visualization. Imagine shrinking the Milky Way so that it fits inside a large stadium, like a major football stadium that seats 100,000 people. At this scale, each star would be smaller than a bacterium, far too small to see with the naked eye, or even with a normal microscope. The distance between neighboring stars would be several meters. You could walk from one invisible star to the next in a few steps, passing through nothing but empty space. The stadium would appear completely empty. If you didn't know better, you'd think there was nothing there at all. And yet this empty-seeming stadium would contain hundreds of billions of stars, each one a massive ball of fusing hydrogen, many with their own planets, moons, and asteroid belts. Stars, massive as they are, occupy only a tiny fraction of galactic volume. If you added up the volume of all the stars in the Milky Way, from the smallest red dwarfs to the largest supergiants, and compared it to the total volume of the galaxy, stars would account for less than a trillionth of the available space. The rest is vacuum. Empty space stretching in every direction, interrupted only occasionally by a star. But even this doesn't capture the true emptiness of the cosmos. We've been talking about the space inside our galaxy. Now let's look at the space between galaxies. The nearest large galaxy to the Milky Way is Andromeda, also known as M31. It's about 2.5 million light-years away. Let me put that in perspective. Even at the speed of light, the fastest speed possible, light from Andromeda takes 2.5 million years to reach us. When you look at Andromeda in the night sky, a faint fuzzy patch visible to the naked eye on a dark night, you're seeing light that left that galaxy 2.5 million years ago. You're looking back in time. The Andromeda you see is Andromeda as it existed when the first members of the genus Homo were just beginning to walk upright in Africa. If you had somehow set out for Andromeda at the speed of light when those first human ancestors appeared, you would just now be arriving. 2.5 million years of travel at the fastest speed the universe allows, and you'd finally reach the nearest large galaxy. The distances are almost inconceivably vast. In our basketball model, where the Sun is a basketball and Proxima Centauri is 4,300 miles away, where is Andromeda? At this scale, things get complicated. The entire Milky Way galaxy, with its hundreds of billions of stars, would need to shrink to about the size of a dinner plate, and Andromeda would be another dinner plate about 15 miles away. The gap between them would be essentially empty, with nothing but occasional atoms of hydrogen drifting through the intergalactic void. The space between galaxies is called intergalactic space. It's the emptiest natural environment in the known universe. While interstellar space within a galaxy contains roughly 1 atom per cubic centimeter, intergalactic space contains less than 1 atom per cubic meter. That's 1,000,000 times emptier than the space between stars. 1,000,000 times emptier than something that was already almost nothing. If you were floating in intergalactic space and collected all the matter from a volume the size of your house, from a volume the size of a large building, you might not find even a single atom. The emptiness is that complete. The void is that perfect. When astronomers map the distribution of galaxies across the observable universe, they find that galaxies aren't spread evenly. They're not scattered randomly like seeds thrown across a garden. Instead, galaxies cluster together along vast filaments and walls, forming what's called the cosmic web. The cosmic web is one of the largest structures in the universe. It consists of filaments of galaxies, long strings of galaxy clusters stretching for hundreds of millions of light years. These filaments connect at nodes where massive galaxy clusters form, and between the filaments, taking up most of the volume of the universe, are enormous voids where almost no galaxies exist. The structure of the cosmic web emerged from tiny fluctuations in the density of matter in the early universe. Right after the Big Bang, Matter was distributed almost uniformly, but there were tiny variations, regions where the density was slightly higher or lower than average. These variations were incredibly small, about 1 part in 100,000. But gravity is patient. Over billions of years, gravity amplified these tiny differences. Regions that were slightly denser attracted more matter, becoming denser still. Regions that were slightly less dense lost matter to their neighbors, becoming emptier. This process continued for billions of years, small differences growing into large ones, until the cosmic web we see today emerged. The filaments are where the matter ended up. The voids are where it came from. Some of these voids are staggeringly large. The Boötes void, discovered in 1981 by astronomer Robert Kirshner and his colleagues, spans about 330 million light-years across. That's more than 3,000 times the diameter of the Milky Way. If our galaxy is a dinner plate, the Boötes void would be a sphere more than a mile in diameter. Inside this void, there are very few galaxies. It's not completely empty. About 60 galaxies have been found within the Boötes void. But a region of that size, based on the average density of galaxies in the universe, should contain about 2,000 galaxies. The void is about 33 times emptier than it should be. If you lived on a planet somewhere in the center of the Boötes void and looked up at the night sky, you would see something profoundly different from what we see on Earth. Our night sky is filled with stars because we're inside a galaxy. The Milky Way stretches across our sky like a river of light on dark nights. We see thousands of individual stars with the naked eye, and millions more with telescopes. From the center of the Boötes void, you would see almost nothing. The nearest galaxies would be over 100 million light-years away. Even with powerful telescopes, they would appear as faint smudges, barely detectable. The sky would be almost completely dark, blacker than any night sky on Earth, punctuated only by the occasional distant galaxy appearing as a tiny spot of light. You would look up and see emptiness. 300 million light-years of essentially nothing in every direction. The loneliness would be absolute. Even larger voids have been discovered. The KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, might be as large as 2 billion light-years across. This is so enormous that some researchers think our own Milky Way might actually be located within it, in a relatively dense region near the edge. If true, this would mean something remarkable. We're living in one of the emptiest large regions of the observable universe. The galaxies we see around us, the cosmic structures we've mapped, all of it exists in a relative void. The universe outside this void is denser than what we see locally. We're in an underdense bubble, surrounded by walls of galaxies we can barely detect. These voids make up the majority of the universe's volume. When astronomers map the cosmic web and calculate what percentage of space is filled by galaxy filaments and clusters versus what percentage is void, the answer is striking. Galaxy filaments and clusters account for only about 20% of the universe's volume. The remaining 80% is void. 4/5 of the universe is essentially empty. Most of the cosmos is vacuum where nothing exists. The galaxies, stars, and planets that make up the visible universe, all the matter we can see and detect, occupies only a small fraction of the available volume. Matter is islands in an ocean of emptiness. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years in diameter. It contains about 2 trillion galaxies. Each of those galaxies contains billions or trillions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That's a 2 followed by 23 zeros. This seems like an almost inconceivable amount of matter. 2 trillion galaxies, 200 billion trillion stars. Surely with that much stuff, the universe must be at least somewhat full. But here's the reality. If you averaged out all the matter and energy in the observable universe, spreading it evenly through all of space, you would end up with a density equivalent to about 5 or 6 hydrogen atoms per cubic meter. That's it. The equivalent of 5 or 6 atoms in a space the size of your closet. Most of the universe is indistinguishable from nothing. To understand how empty this is, consider what it would be like to exist at this density. Right now, you're surrounded by air containing quintillions of molecules per cubic centimeter. Every breath you take contains trillions of atoms. The air feels substantial even though you can't see it. If you were floating in space with matter spread at the cosmic average density, you'd be in an environment about 49 orders of magnitude emptier than the air you're breathing. That's a 1 followed by 49 zeros times emptier. The difference between the air in your lungs and the cosmic average density is larger than the difference between a single atom and the entire observable universe. At this density, if you collected all the atoms in a cube, 1 astronomical unit on each side, a cube large enough to contain Earth's entire orbit around the Sun, you'd have about 3 grams of hydrogen. That's about the mass of 3 paperclips, spread across a volume 93 million miles wide. This is the fundamental nature of the cosmos. Empty space is the default state. Matter is the exception, the anomaly, the rare interruption in the void. For every atom that exists, there's an enormous volume of empty space where no atoms are. And this emptiness isn't static. It's growing. The universe is expanding. In 1929, astronomer Edwin Hubble made one of the most important discoveries in the history of science. He found that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it's receding. This relationship, now called Hubble's law, revealed that the universe is expanding. But it's not that galaxies are flying apart through space like shrapnel from an explosion. It's that space itself is stretching. The fabric of the universe is expanding, carrying galaxies apart like dots on the surface of a balloon being inflated. The galaxies aren't moving through space. Space itself is growing, and the galaxies are going along for the ride. This means the voids are getting larger. The gaps between galaxy clusters are widening. More and more emptiness is being created all the time. Every second, the universe becomes emptier than it was before. And in 1998, astronomers made an even more startling discovery. The expansion of the universe isn't slowing down, as everyone expected. It's speeding up. Something is pushing the universe apart, making it expand faster and faster over time. We call this mysterious force dark energy, and whatever it is, there's a lot of it, far more than all the ordinary matter in the universe combined. No one knows what dark energy is. It might be energy inherent to empty space itself. It might be some new force we don't yet understand. But whatever it is, it's causing the universe to expand at an accelerating rate, creating more emptiness faster than ever before. In the distant future, this acceleration will have profound consequences. Galaxies that are visible today will be carried beyond our cosmic horizon. Their light will never reach us because space between us and them will be expanding faster than light can cross it. The light will try to reach us, but it will be like trying to walk up a down escalator that's moving faster than you can walk. The light will never arrive. Eventually, far in the future, observers in our galaxy will look out and see only darkness in every direction. All the other galaxies will have been carried away by the expansion of space. The universe will appear to contain only one galaxy, our own, surrounded by infinite, expanding void. The loneliness that exists today in the center of the Botess void will become the universal condition. But we're getting ahead of ourselves. We still have much more to explore about the emptiness that fills the cosmos. We've established that space is almost perfectly empty. From the gaps between planets to the voids between galaxies, emptiness dominates at every scale. But what exactly is this empty space? Is it truly nothing? Or is there something there, even in the most perfect vacuum? For centuries, scientists assumed that empty space was simply absence. Where matter isn't, there's nothing. The vacuum is void. End of story. But modern physics has revealed something surprising. Empty space isn't empty at all. The nothing of the vacuum turns out to be far stranger and more interesting than mere absence. Even in the most perfect vacuum, where every atom has been removed and nothing visible remains, something is still there. The vacuum is alive with activity, filled with quantum fields and virtual particles, buzzing with energy that affects everything in the universe. In the next section, we'll dive into the physics of emptiness. We'll explore what scientists have discovered about the true nature of nothing. We'll learn about quantum fluctuations, virtual particles, and the energy of empty space. And we'll see how this not quite nothing might actually be one of the most important things in the universe, shaping the cosmos from the Big Bang to the ultimate fate of everything that exists. We've seen that the universe is mostly empty space. From the interior of atoms to the vast gulfs between galaxies, emptiness dominates at every scale we've examined. Atoms are more than 99% void. The space between planets is nearly perfect vacuum. Interstellar space contains only one atom per cubic centimeter. Intergalactic space is 1,000,000 times emptier still. And the cosmic voids between galaxy clusters stretch for hundreds of millions of light years with almost nothing inside them. But now we need to ask a deeper question, perhaps the deepest question of all. What exactly is empty space? What is nothing, really? This might seem like a strange question. Nothing is nothing. What else could it be? An empty box is empty. A cleared table has nothing on it. The space where something used to be is now vacant. We use the concept of nothing constantly in everyday life, and we think we understand it perfectly. But physics has revealed something astonishing about empty space. The nothing of the vacuum isn't really nothing at all. It's actually one of the strangest and most active things in the entire universe. And understanding what nothing really is takes us to the very frontier of human knowledge. For most of human history, the answer to what nothing is seemed obvious. Nothing is simply the absence of something. Empty space is the blank canvas on which the universe paints its picture. The vacuum has no properties because there's nothing there to have properties. Nothing is, by definition, the lack of anything. The ancient Greek philosopher Aristotle, one of the most influential thinkers in Western history, famously argued that true emptiness was actually impossible. Nature abhors a vacuum, he said. Where matter is removed, something must rush in to fill the gap. Air flows into an emptied container. Water rises to fill a void. The universe, Aristotle believed, was fundamentally full. Emptiness couldn't exist because the cosmos wouldn't allow it. For nearly 2,000 years, this view dominated Western thought. Scholars accepted Aristotle's arguments. The vacuum was impossible, and discussions about nothing were largely philosophical rather than scientific. But beginning in the 17th century, scientists started to question this ancient assumption. In 1654, a German scientist named Otto von Guericke invented the air pump. He demonstrated dramatically that air could be removed from a container, creating a partial vacuum inside. In his most famous experiment, he created two large copper hemispheres that fit together, pumped the air out from between them, and then showed that teams of horses pulling in opposite directions couldn't separate them. The vacuum inside was real, and it exerted real force. Robert Boyle in England improved on these experiments. He showed that sound couldn't travel through a vacuum, proving that sound needs a medium to propagate. But light could travel through a vacuum. passing through the emptied glass containers without difficulty. This suggested that light was fundamentally different from sound, a distinction that would eventually lead to our modern understanding of electromagnetic radiation. Gradually, the idea of empty space as something real and possible took hold in scientific thinking. By the 19th century, physicists had developed a sophisticated understanding of the vacuum. It was simply the absence of matter. Take away all the atoms from a region of space, and what remains is emptiness. The vacuum was considered a passive background, a stage on which the drama of physics played out. The vacuum itself did nothing. It was nothing. But then came the 20th century, and everything we thought we knew about nothing had to be revised. Modern physics tells us that empty space isn't really empty at all. Even in the most perfect vacuum imaginable, even in a region where every single atom has been removed and nothing visible remains, something is still there. The nothing of the quantum vacuum is far stranger, far more active, and far more important than scientists ever imagined. Let's start with what physicists call quantum field theory. This is the framework that underlies our modern understanding of particle physics, and it has been tested to extraordinary precision. Quantum field theory describes a universe that is fundamentally different from what our everyday intuition suggests. According to quantum field theory, the universe is filled with fields. These fields aren't made of anything. They're not composed of particles or atoms or any other substance. They're fundamental aspects of reality itself, woven into the fabric of existence. These fields exist everywhere, extending through all of space, permeating every region of the universe, even the emptiest voids between galaxies. You're probably familiar with at least one field, the electromagnetic field. This field pervades all of space. It exists right where you're sitting. It exists in the deepest reaches of intergalactic space. It exists everywhere. When the electromagnetic field is undisturbed, when it's in its lowest energy state, you don't notice it. It's there, but it's not doing anything obvious. But when the field is excited, when it vibrates in certain ways, those vibrations are what we call photons, particles of light. Here's the key insight. A photon isn't a separate thing that exists in space, floating around independently like a tiny ball. A photon is a ripple in the electromagnetic field. It's a wave, a disturbance, an excitation of the underlying field. Think of it like a wave on the surface of a pond. The wave isn't separate from the water. The wave is the water, disturbed and moving in a particular pattern. Similarly, a photon is the electromagnetic field, vibrating in a particular way. The same is true for all particles. Electrons are ripples in the electron field. Quarks are ripples in various quark fields. The Higgs boson, discovered at the Large Hadron Collider in 2012 after decades of searching, is a ripple in the Higgs field. Every type of particle we've ever detected corresponds to a quantum field that extends through all of space. This changes how we think about empty space. When we say a region of space is empty, what we mean is that the fields in that region are in their ground state, their lowest energy configuration. No particles are present because the fields aren't vibrating in ways that produce particles, but the fields themselves are still there. They're always there. They never go away. A particle is just an excitation of a field, like a wave on the ocean. When there are no particles, the ocean is calm, but the ocean still exists. When we pump all the air out of a container and create a vacuum, the electromagnetic field is still there. The electron field is still there. The quark fields and the Higgs field and all the other fields that make up reality are still there. The container isn't truly empty. It's full of fields in their ground state. So is a region with no particles but with fields truly nothing? Or is it something? This is where the quantum vacuum becomes deeply strange. In classical physics, the physics that Newton developed and that works perfectly well for everyday situations, the vacuum would have zero energy. If there are no particles, there's no energy. The fields are calm, nothing is happening, and the energy is exactly zero. Simple and intuitive. But quantum mechanics forbids this. One of the foundational principles of quantum mechanics is called the Heisenberg uncertainty principle, discovered by German physicist Werner Heisenberg in 1927. This principle puts a fundamental limit on how precisely certain pairs of properties can be simultaneously known. You cannot simultaneously know both the exact position and the exact momentum of a particle. You cannot simultaneously know both the exact energy of a system and the exact time at which that energy is measured. The more precisely you know one quantity, the less precisely you can know the other. This isn't a limitation of our measuring instruments. It's a fundamental feature of reality. The universe itself doesn't have definite values for both properties at once. This uncertainty applies to empty space in a profound way. You might think that in a perfect vacuum, the energy would be exactly zero. After all, there's nothing there. How could there be any energy? But the uncertainty principle says you can't be certain of that. If the energy were exactly zero, you would know the energy with perfect precision. The uncertainty in energy would be zero. But this would violate the uncertainty principle, which requires that energy and time have a minimum combined uncertainty. The result is that energy must fluctuate. It must jiggle randomly around some average value. You can never pin the energy of empty space down to exactly zero, because that would violate a fundamental law of physics. Even in the emptiest possible vacuum, the energy is constantly flickering up and down in tiny random amounts. These fluctuations are called quantum fluctuations, or vacuum fluctuations. They happen everywhere, all the time, even in the emptiest regions of space. The energy of the vacuum is never exactly zero. It's constantly jittering, going up and down, never quite settling to a fixed value. Here's where things get truly bizarre. These energy fluctuations can briefly create particles out of nothing. The uncertainty principle allows energy to be borrowed from the vacuum for brief periods. The larger the amount of energy borrowed, the shorter the time it can exist before the debt must be repaid. A small amount of energy can exist for a longer time. A large amount can exist only for an incredibly brief instant. This means that pairs of particles can pop into existence out of the vacuum, exist for a fleeting moment, and then annihilate each other, returning their borrowed energy to the void. These are called virtual particles. They're not virtual in the sense of being imaginary or fake. They're virtual in the sense that they can never be directly observed as individual particles. They exist for too short a time and their effects cancel out. In the quantum vacuum, this is happening constantly. An electron and a positron, the electron's antiparticle, appear out of nothing. They exist for an incredibly brief moment, a time span so short it's measured in fractions of a trillionth of a second. Then they collide and annihilate, vanishing back into the vacuum. A quark and an antiquark flash into existence and immediately cancel each other out. A photon briefly appears and disappears. This happens constantly, everywhere, including right where you're sitting right now. The space around you is buzzing with virtual particles appearing and disappearing billions of times per second. They emerge in pairs because certain quantities like electric charge must be conserved. A positively charged particle always appears with a negatively charged partner. The total charge remains zero. The total energy balances out. But in between creation and annihilation, the particles briefly exist. You can't see them. You can't detect them individually because they exist for such a short time and their effects average out to zero. They're called virtual because they can never be isolated and measured. But they're there. The vacuum is alive with activity, seething with particles that flicker in and out of existence like static on a television screen. This might sound like theoretical speculation, like physicists inventing invisible particles to make their equations work. But we have experimental evidence that virtual particles are real. The evidence comes from something called the Casimir effect. The Casimir effect was predicted by Dutch physicist Hendrik Casimir in 1948. Casimir realized that if virtual particles really exist, they should produce a measurable force under the right conditions. Here's how it works. Take two metal plates and place them very close together in a vacuum. When I say very close, I mean separated by only a few hundred nanometers. A nanometer is a billionth of a meter, so a few hundred nanometers is a few hundred billionths of a meter. This is an incredibly small gap, much smaller than the width of a human hair. Between these plates, the space is so small that only certain wavelengths of virtual particles can fit. Think about waves on a guitar string. A guitar string is fixed at both ends, so only certain wavelengths of vibration are possible. The wavelength must fit neatly between the two ends, with a node at each boundary. Similarly, between two metal plates, only certain wavelengths of virtual particles can exist. The wavelength must fit between the plates. Outside the plates, in the open vacuum, there's no such restriction. All wavelengths are allowed. Any virtual particle can exist there. This creates an imbalance. There are more virtual particles, more vacuum fluctuations, outside the plates than between them. The outside has more energy than the inside. This difference creates a pressure, a tiny but real force that pushes the plates together. The Casimir effect was confirmed experimentally in 1997 by physicist Steve Lamoureux at Los Alamos National Laboratory. He measured the force between two carefully prepared plates and found exactly what Casimir had predicted nearly 50 years earlier. The force is incredibly small. For plates 1 square centimeter in area separated by 1 micrometer, the force is about 100 billionth of a Newton. You'd never notice it in everyday life, but with sensitive enough equipment, it's measurable. And it's been measured repeatedly by multiple teams using different techniques, with results that match theoretical predictions to high precision. The Casimir effect proves that the vacuum has energy. Empty space exerts a real, physical force because of the virtual particles it contains. The nothing of the vacuum is doing something. It's pushing those plates together. Nothing, it turns out, is something. The energy of the quantum vacuum is called zero-point energy. Even at absolute zero, the coldest temperature possible, the point where all thermal motion has ceased, and atoms are as still as they can be, the vacuum still has energy because of quantum fluctuations. You can never remove all the energy from a region of space. There's a minimum, a floor, a baseline that can't be breached because the uncertainty principle won't allow it. How much zero-point energy is there in the vacuum? This is where things get complicated and, frankly, rather embarrassing for theoretical physics. When physicists calculate the expected energy density of the vacuum based on quantum field theory, the calculation involves adding up the zero-point energy of all the possible wavelengths of all the quantum fields. When you do this, the sum doesn't converge to a nice finite number. It goes to infinity. Obviously, infinite energy in every cubic centimeter of space can't be right. Something is wrong with the calculation. Physicists deal with this by introducing a cutoff, a maximum energy or minimum wavelength beyond which the calculation stops. A natural choice for this cutoff is called the Planck scale, named after physicist Max Planck. The Planck scale is the distance at which quantum effects and gravity become equally important. It's incredibly small, about 10 to the negative 35 meters. At this scale, our current theories break down anyway. We don't have a working theory of quantum gravity, so it makes sense to stop the calculation before we reach that point. Even with this cutoff, the predicted vacuum energy is enormous, about 10 to the power of 113 joules per cubic meter. That's a 1 followed by 113 zeros. To put this in perspective, this is more energy in a single cubic meter of vacuum than exists in all the matter in the entire observable universe combined. If this prediction were correct, the universe would look completely different from what we observe. The enormous vacuum energy would curve space-time so dramatically that stars and galaxies couldn't exist. The universe would have torn itself apart or collapsed almost instantly after the Big Bang. But when we observe the actual universe, when we measure the behavior of empty space based on how the cosmos expands and evolves, we find something different. The vacuum energy is not zero. We can measure its effects. But it's also not anywhere near the theoretical prediction. The observed value is about 10 to the power of -9 joules per cubic meter. That's 120 orders of magnitude smaller than what quantum field theory predicts. 120 zeros difference between prediction and observation. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in all of physics. No one knows why the vacuum energy is so much smaller than predicted. Something is clearly wrong with either our theories or our understanding, but no one has figured out what. Various explanations have been proposed. Some involve supersymmetry, a theoretical framework that predicts every known particle has a heavier partner particle. The contributions from these partner particles might cancel out some of the vacuum energy. Others involve extra dimensions of space beyond the three we experience. Still others invoke something called the anthropic principle, which suggests that the vacuum energy is small in our universe, because if it were large, galaxies couldn't form and we wouldn't be here to measure it. None of these explanations has been confirmed. The cosmological constant problem remains unsolved, a major gap in our understanding of nature. What we do know is that the vacuum does have some energy, and that energy has real effects. In fact, vacuum energy might be responsible for the most dramatic phenomenon in modern cosmology, the accelerating expansion of the universe. In 1998, two independent teams of astronomers made one of the most surprising discoveries in the history of science. One team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory in California. The other was led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University. They didn't know about each other's work. They were doing the same experiment independently. Both teams were measuring distances to faraway supernovae, exploding stars that can be seen across billions of light years. Supernovae of a particular type, called Type Ia supernovae, all have about the same intrinsic brightness. By comparing how bright a supernova appears to how bright it actually is, astronomers can calculate how far away it is. This allows them to map the expansion history of the universe. Both teams expected to find that the expansion was slowing down over time. This seemed natural. Gravity is attractive. All the matter in the universe pulls on all the other matter, like a giant web of rubber bands connecting everything. This gravitational attraction should gradually decelerate the expansion that began with the Big Bang. The universe should be coasting, losing momentum as gravity slowly reels everything back in. The question was how much the expansion was slowing. Was it slowing quickly, which would mean the universe would eventually stop expanding and collapse back on itself? Or was it slowing slowly, which would mean the universe would expand forever but at an ever-decreasing rate? What both teams found shocked the scientific world. The expansion isn't slowing down at all, it's speeding up. The universe is accelerating, with distant galaxies moving away from us faster and faster over time. This discovery earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. It was one of the most important astronomical discoveries of the 20th century, but it also created a major puzzle. Something must be pushing the universe apart. Some force or energy must be overcoming the attractive pull of gravity, causing space to expand faster and faster. But what? We call this mysterious, something dark energy. We don't know what it is. We can't see it or detect it directly, but we can measure its effects. And based on those measurements, dark energy makes up about 68% of the total energy content of the universe. Whatever dark energy is, there's a lot of it. more than everything else combined. One possibility is that dark energy is vacuum energy, the zero-point energy of empty space. If the vacuum has energy, and if that energy has a particular property that physicists call negative pressure, then it would cause space itself to expand. Here's how this would work. Normal matter has positive pressure. It pushes outward, like air in a balloon. Positive pressure combined with gravity tends to make things contract, to pull inward. But vacuum energy, if it exists in the form we suspect, would have negative pressure. Instead of pushing outward, it would effectively pull inward on itself while still causing space to expand. This sounds paradoxical, but it's a consequence of Einstein's equations of general relativity. The result would be exponential expansion. The more space there is, the more vacuum energy there is, because every region of space contains vacuum energy. And the more vacuum energy there is, the faster space expands. This creates more space, which contains more vacuum energy, which causes faster expansion. It's a runaway process, a feedback loop where emptiness creates more emptiness. This would mean that the nothing filling the universe is actually driving its ultimate fate. The emptiness between galaxies isn't passive, it's active. It's pushing things apart. The void is literally making more of itself. But vacuum energy doesn't just affect the distant future. It also shaped the distant past, in the very first moments after the Big Bang. In the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion called cosmic inflation. This theory was first proposed by physicist Alan Guth in 1980, and it has become a cornerstone of modern cosmology. Inflation solves several puzzles about the universe that would otherwise be very difficult to explain. During inflation, in less than 10 to the power of negative 36 seconds, the universe expanded by a factor of at least 10 to the power of 26. Let me try to put this in perspective. Imagine taking something smaller than a proton, a subatomic particle far too small to see, and expanding it until it's larger than the entire observable universe is today. And doing this in a time shorter than it takes light to cross a proton. That's how fast and how dramatic inflation was. What drove this incredible expansion? Physicists believe it was a form of vacuum energy associated with a field called the inflaton field. In the earliest moments of the universe, this field was displaced from its minimum energy state. It was perched in a high-energy configuration, like a ball sitting at the top of a hill. This configuration had enormous energy density, which caused space to expand exponentially. Then the field decayed, rolling down to its minimum energy state like a ball rolling down a hill into a valley. As it did, its energy was released as the particles and radiation that would eventually become all the matter in the universe. Inflation ended, and the normal hot Big Bang evolution began. Here's the remarkable part that connects everything we've discussed. During inflation, quantum fluctuations in the vacuum were stretched to cosmic scales. Remember quantum fluctuations, the tiny random variations in energy caused by the uncertainty principle. During inflation, the universe was expanding so fast that these microscopic fluctuations were stretched enormously. Variations that started at the subatomic scale were expanded until they spanned millions and eventually billions of light years. These stretched fluctuations became the seeds of all structure in the universe. They created regions where the density of matter was slightly higher or lower than average. Over billions of years, gravity amplified these small differences. Denser regions attracted more matter and became denser still. Less dense regions lost matter and became voids. The cosmic web, the largest structure in the universe, the filaments and walls and voids that span billions of light years, all of it originated as quantum fluctuations in the vacuum during the first tiny fraction of a second of cosmic history. The nothing of empty space, through the strange rules of quantum mechanics, created the patterns that would eventually become everything. Every galaxy traces back to a quantum fluctuation. Every star, every planet, every living thing, all of it exists because of random jitters in the vacuum nearly 14 billion years ago. The seeds of our existence were planted in the void. Empty space isn't just passive background. It isn't just the stage on which the drama of the universe unfolds. Empty space is an active participant in that drama. The vacuum has energy. It creates virtual particles. It drives cosmic expansion. It seeded the structures we see today. Nothing, properly understood, is actually something very important. This raises a philosophical question that has puzzled thinkers for millennia. What is nothing, really? Can true nothing exist at all? In everyday language, nothing is simple. Nothing is the absence of something. An empty box contains nothing. A blank page has nothing written on it. We use the concept casually, and we think we understand it. But physics suggests that this everyday notion of nothing might be impossible to achieve in the real universe. Even the emptiest region of space, even the deepest intergalactic void, billions of light years from the nearest galaxy, contains quantum fields. These fields exist everywhere. They permeate all of space. They never go away. And those fields have energy, even in their ground state. They host virtual particles that constantly pop in and out of existence. True nothing, a region with no fields and no energy and no activity at all, doesn't seem to exist anywhere in the universe. We can't create it in our laboratories. We can't find it in the cosmos. Every region of space we've ever examined, no matter how empty, still contains something. Some physicists argue that true nothing would have to be the absence of space and time themselves. Not empty space, but no space at all. Not a vacuum, but the absence of even the vacuum. Before the Big Bang, according to some theories, there was no space, no time, no fields, no dimensions, no properties of any kind, just true nothing. And then, somehow, something emerged from that nothing. But can something come from nothing? This is where physics shades into philosophy and perhaps into questions that science alone cannot answer. Some argue that the universe must have had a cause, something that brought it into being. Others argue that the universe might have no cause, that it simply exists as a brute fact, requiring no explanation. Still others suggest that the quantum properties of the vacuum might allow something to spontaneously emerge from nothing, that the rules of quantum mechanics might apply even to the question of existence itself. These are deep waters. We're at the edge of what science can currently tell us. What we can say scientifically is that in the universe as it exists today, true nothing doesn't seem to exist anywhere. Every region of space contains fields. Every vacuum seethes with virtual particles. The energy of emptiness is never exactly zero. The nothing we encounter in everyday life, the empty boxes and vacant rooms, is always actually something when examined at the quantum level. The science of nothing turns out to be the science of something after all. The void is not void. Emptiness is full of activity. And the nothing that fills most of the universe is actually one of its most important and mysterious components. Understanding nothing is essential to understanding everything. In our final section, we'll explore what all of this means. Why does it matter that nothing is actually everywhere? What are the implications for our understanding of the universe and our place within it? And is there something profound, even beautiful, about the fact that existence itself is built upon a foundation of emptiness? We've traveled an extraordinary distance together tonight. We started inside atoms, discovering that the very substance of matter is more than 99% emptiness. We zoomed out through the solar system, finding near-perfect vacuum between the planets. We ventured into interstellar space, where single atoms drift through cubic centimeters of nothing. We crossed the gulfs between galaxies, the emptiest natural environments in existence, and we dove into the quantum vacuum, discovering that even perfect emptiness seethes with virtual particles and energy. Now, let's step back and ask the question that matters most. Why should we care? What does it mean that nothing is actually everywhere? And how should we feel about living in a universe that is fundamentally, overwhelmingly empty? At first glance, the emptiness of the universe might seem depressing. We like to feel substantial. We like to feel solid and real. We like to think that the world around us is made of something, that the ground beneath our feet has genuine presence, that the people we love have real substance. Learning that everything, including our own bodies, is more than 99% empty space can feel destabilizing. It can make reality seem less real somehow. Learning that the cosmos is mostly void, with matter scattered like dust motes in an empty warehouse that stretches for billions of light years, can feel lonely. We're not just small. We're small and surrounded by almost infinite emptiness. The nearest star is 4 light years away through vacuum. The nearest large galaxy is 2.5 million light years distant. We exist on a tiny rock orbiting an ordinary star in one galaxy among trillions, and most of the space between all of these objects contains essentially nothing. Some people find this deeply unsettling. They preferred the old view, the intuitive view, where the world was solid and substantial and full of stuff. They don't want to know that their hand has never actually touched anything, that the sensation of solidity is electromagnetic repulsion, that the chair supporting them is mostly void. But I want to suggest a different perspective. The emptiness of the universe isn't a flaw or a disappointment. It isn't a cosmic mistake or a sign that something went wrong. The emptiness is actually essential. Without all that nothing, there could be no something. The void isn't opposed to existence. The void is what makes existence possible. Consider what the universe would be like if there were no empty space at the atomic level. Imagine if atoms were solid balls of matter with no gaps, no room for electrons to orbit, no emptiness between the nucleus and the outer reaches of the atom. What would happen in such a universe? For one thing, atoms couldn't bond with each other. Chemical bonds, the connections that hold molecules together, form because electrons can be shared or transferred between atoms. When 2 hydrogen atoms bond with an oxygen atom to form water, electrons are being shared across the space between nuclei. When sodium and chlorine form table salt, an electron is being transferred from one atom to another. These processes require space for electrons to move through. Without empty space inside atoms, chemistry as we know it wouldn't exist. No chemistry means no molecules, no water, no carbon compounds, no amino acids or proteins or DNA, no sugars or fats or vitamins. Everything that makes life possible depends on atoms bonding together in complex ways. Without the emptiness inside atoms, none of these bonds could form. Life would be impossible. Not just human life, any life. The universe would be chemically dead. The emptiness inside atoms also allows for the storage and transfer of energy, which is fundamental to everything that happens in the universe. When an electron absorbs energy, it moves to a higher orbit, farther from the nucleus. The atom stores that energy in the new configuration. When the electron releases energy, it drops to a lower orbit and emits a photon, a particle of light. This is how atoms absorb and emit light. This process is everywhere. It's how solar panels work. Photons from the sun hit atoms in the solar panel, exciting electrons and allowing energy to be captured. It's how photosynthesis works. Plants absorb sunlight and use that energy to build complex molecules from simple ones. It's how your eyes work. Photons enter your eye and excite electrons in the molecules of your retina, triggering nerve signals that your brain interprets as vision. The gaps inside atoms are where these energy transactions happen. The emptiness provides room for electrons to move up and down between energy levels, absorbing and releasing photons as they go. Without that emptiness, without that space for electrons to occupy different orbits, none of this would be possible. There would be no light absorption, no energy transfer, no vision, no photosynthesis, no life. Without the emptiness inside atoms, the universe would be cold, static, and dead. No chemistry, no energy flow, no complexity, just solid, inert matter doing nothing forever. Now consider what the universe would be like if there were no empty space between objects. Imagine if matter filled all of space uniformly, with no gaps, no voids, no emptiness anywhere. What would happen then? For one thing, nothing could move. Movement requires empty space to move into. A fish can swim because the water in front of it can get out of the way, flowing around the fish's body. You can walk because the air around you is mostly nothing, offering little resistance to your passage. A planet can orbit its star because there's empty space to orbit through, vacuum that offers no friction or resistance. In a universe filled completely with matter, nothing could change position. Everything would be locked in place forever. Atoms couldn't vibrate, planets couldn't orbit, rivers couldn't flow, wind couldn't blow, hearts couldn't beat, blood couldn't circulate, thoughts couldn't form, because thoughts require neurons firing, which requires ions moving, which requires space for those ions to move through. Everything would be frozen. Not frozen in the sense of being cold, but frozen in the sense of being utterly immobile. Nothing could happen because nothing could move. But it's even worse than that. In a universe without empty space, there would be no time as we experience it. Think about what time actually is. Our sense of time passing comes from things changing, from events happening, from before and after being different. The clock ticks. The sun moves across the sky. Your heart beats. Your thoughts flow from one to the next. Without the possibility of movement or change, there would be no events. Nothing would happen, ever. There would be no processes, no cause and effect, no sequence of moments. Physics itself would cease to exist in any meaningful sense. The universe would be a frozen, eternal block of matter where nothing happens and nothing can happen. The emptiness of the universe allows for change, for movement, for complexity, for life, for thought, for us. The void is what makes the dance possible. Now consider the cosmic scale. The vast voids between galaxies seem like wasted space, hundreds of millions of light years of essentially nothing. What possible purpose could all that emptiness serve? It turns out the cosmic voids serve essential purposes. They're not wasted space at all. The expansion of the universe, driven partly by the energy of empty space itself, gives the cosmos time to evolve. Think about what would happen if the universe weren't expanding. All the matter in the universe attracts all the other matter through gravity. If the universe were static, if space weren't expanding, this gravitational attraction would pull everything together. The universe would collapse. This isn't speculation. We can calculate how long a static universe would last before gravity pulled it all back together. The answer is not very long by cosmic standards. Without expansion, the universe would have collapsed back into a singularity long before stars or planets or life ever had a chance to form. Everything would have ended almost as soon as it began. The expansion of space is what prevents this gravitational collapse. As space expands, it carries galaxies apart, counteracting the inward pull of gravity. This gives the universe time. Time for stars to form, time for those stars to fuse hydrogen into heavier elements, time for those stars to explode as supernovae, scattering their heavy elements into space, time for new stars to form from that enriched debris, time for planets to coalesce around those stars, time for chemistry to grow complex, time for life to emerge and evolve. Stars need billions of years to forge the heavy elements that make up rocky planets and living things. The carbon in your body was made in a star that lived and died before our sun was born. The iron in your blood was created in a supernova explosion billions of years ago. Creating these elements takes time, lots of time. Planets need hundreds of millions of years to form from the debris left over after star formation. They start as grains of dust that collide and stick together, gradually building up to pebbles, then boulders, then planetesimals, then planets. This process can't be rushed. Life needs hundreds of millions more years to evolve from simple chemistry to complex organisms. The first life on Earth appeared about 3.8 billion years ago. Complex multicellular life didn't emerge until about 600 million years ago. Humans have been around for only about 300,000 years. Evolution is slow. The expanding universe, the increasing amount of nothing between galaxy clusters, is what provides all this time. The void gives the universe room to breathe, room to evolve, room to become interesting. The voids between galaxies also allow for the formation of structure. Remember the cosmic web, that vast pattern of filaments and walls and voids that spans the observable universe. Galaxies cluster along the filaments. The voids are where matter flowed away from. This structure formed because matter could move. In the early universe, tiny density fluctuations provided the seeds. Regions that were slightly denser attracted more matter through gravity, becoming denser still. Regions that were slightly less dense lost matter to their neighbors, becoming voids. Over billions of years, this process amplified small differences into the enormous cosmic structures we see today. This process required empty space. Matter needed room to flow from the less dense regions to the denser ones. Without that room, without that emptiness, matter couldn't have moved. The cosmic web couldn't have formed. The universe would have remained uniform soup, the same everywhere, with no galaxies, no stars, no planets, no islands of complexity in the cosmic ocean. Without the voids, without the ability for matter to cluster and separate, we wouldn't exist. Empty space made structure possible. Structure made us possible. Empty space isn't just absence. It's possibility. It's the room in which things can happen. It's the canvas on which the universe paints its picture. It's the silence that makes the music possible. There's also something to be said about the beauty of emptiness, because beauty matters too. The night sky is beautiful precisely because of the contrast between the stars and the dark void surrounding them. Points of light scattered across infinite darkness. The Milky Way stretching overhead like a river of light through the black. If the sky were uniformly bright, if there were no darkness, we'd see no stars, we'd see no constellations that humans have named and told stories about for thousands of years. We'd see no Milky Way arching across the heavens. The darkness, the emptiness, is what lets us see the light. The nothing reveals the something. The void gives the stars their meaning. The same is true at every scale. The gaps between atoms allow for the intricate structures of molecules. DNA's double helix works because atoms can be arranged in specific three-dimensional patterns with spaces between them. The spaces between cells allow for the organization of tissues. Your organs work because cells can be arranged in complex ways with gaps for blood vessels and nerves and structural fibers. The distances between planets allow for stable orbits. If Earth were much closer to Jupiter, Jupiter's gravity would have flung us out of the solar system long ago. The voids between galaxies allow for the cosmic web. At every level of reality, from atoms to the observable universe, emptiness enables structure. Without the nothing, the something couldn't organize itself into anything interesting. Let me tell you about the far future, because the emptiness of the universe will become even more profound as time goes on. This is a story with a melancholy ending, but also with meaning if we look for it. The universe is about 13.8 billion years old. That sounds ancient by human standards, but it's actually quite young by cosmic standards. Stars have been forming and dying for most of that time, creating heavy elements in their cores and scattering them into space when they explode. This ongoing cycle of stellar birth and death has seeded galaxies with the raw materials for planets and life, but star formation won't last forever. The raw material for new stars is hydrogen gas, the simplest element, left over from the Big Bang. When the universe was young, hydrogen was everywhere. Vast clouds of it filling space, ready to collapse under gravity and ignite into new stars. But as stars form, they convert hydrogen into heavier elements. Helium, carbon, oxygen, iron. This process is essentially one way. Fusion builds heavy elements from light ones, but there's no natural process that breaks heavy elements back down into hydrogen. So the supply of hydrogen is slowly, inexorably being depleted. In about 100 trillion years, give or take, the last stars will have formed and burned out. The universe will go dark. No more stellar furnaces converting hydrogen to light and heat. No more warmth radiating from nuclear fusion. Just darkness stretching in all directions. What will remain? Stellar remnants? White dwarfs, the cooling embers of stars like our sun, will slowly fade over trillions of years, radiating away their stored heat until they become cold black dwarfs, invisible spheres of degenerate matter. Neutron stars will spin down, their magnetic fields decaying, their rapid rotation slowing to a halt. Black holes will drift through space, slowly growing as they absorb any matter that wanders too close. In this far future, the emptiness between objects will be even more extreme than today. The universe will have continued expanding the whole time. Galaxy clusters that are relatively close today will have been carried apart by the expansion of space. The sky will be almost completely dark. An observer in this era would look out and see almost nothing, just a few dim stellar remnants in their own merged galactic structure, surrounded by an infinite-seeming void. Eventually, in the very far future, even these remnants will disappear. Black holes will evaporate through a process called Hawking radiation. Stephen Hawking showed in 1974 that black holes aren't completely black. Quantum effects near the event horizon cause black holes to emit radiation very slowly, losing mass particle by particle over enormous spans of time. A black hole with the mass of our sun would take about 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. A supermassive black hole like the one at the center of our galaxy, with a mass of about 4 million suns, would take about 10 to the power of 100 years to evaporate. Let me try to give you some sense of how unimaginably long that is. The universe is currently about 10 to the power of 10 years old, about 14 billion years. 10 to the power of 100 is 10 to the power of 90 times longer than the current age of the universe. If you multiplied the current age of the universe by itself 90 times, you'd get a number approaching how long it takes for the largest black holes to evaporate. In that ultimate future, after the last black holes have evaporated, the universe may contain nothing but a thin, cold sea of photons and subatomic particles drifting through ever-expanding space. The temperature will approach absolute zero. So little will be happening that change itself becomes meaningless. Time may lose its meaning when nothing happens to mark its passage. This is called heat death. It's the ultimate triumph of nothing over something. The universe that started as an incredibly hot, dense state will end as a cold, dilute whisper, barely distinguishable from true emptiness. The void will have won. Some find this vision of the future bleak. Everything we are, everything we've built, every memory and hope and dream will ultimately be erased by the expanding void. In the end, nothing will remain. The emptiness will be complete. But consider another perspective. Heat death is unfathomably far in the future. We are living in the extreme youth of the cosmos, in the morning hours of a day that will last longer than we can comprehend. The interesting part, the part with stars and planets and chemistry and life, has barely begun. Worrying about heat death is like worrying about the end of a movie when the opening credits are still rolling. We have time. Incomprehensible amounts of time. And in this brief early moment, in this sliver of cosmic time when stars still shine and matter still clumps and complexity still emerges, we exist. After billions of years of cosmic evolution, consciousness has arisen. Minds have formed that can contemplate the universe and their place in it. Beings have emerged who can wonder about the void and feel awe at its vastness. That's remarkable. Out of empty space and quantum fluctuations and gravity and chemistry, the universe has produced something that can look back at itself and understand. You are the universe contemplating itself. You are organized matter, wondering about the void from which it came. The emptiness of the universe, which will ultimately encompass everything, is also what gave us the time and space to exist in the first place. We are children of the void. We owe our existence to the nothing that surrounds us. Without the emptiness, the universe would have collapsed long ago. Without the emptiness, matter couldn't have moved and organized and become complex. Without the emptiness, chemistry couldn't work and life couldn't exist. The void is not our enemy. The void is our origin. We emerged from it. We exist within it. And we will eventually return to it. But in between, we get to experience existence. We get to love and wonder and create and explore. We get to look up at the stars and feel something. Your body is more than 99% empty space. The atoms that make you up are almost entirely nothing. The space between those atoms is mostly void. And yet here you are, thinking, feeling, reading or listening to these words, and contemplating your place in the cosmos. The emptiness inside you has organized itself into something that can contemplate its own existence. That's not depressing. That's miraculous. That's the most remarkable thing the universe has ever done. From almost perfect emptiness, from void and vacuum and quantum fluctuations, complexity has emerged. Consciousness has emerged. You have emerged. The matter that makes up your body was forged in the hearts of stars that exploded billions of years ago. Carbon, oxygen, nitrogen, iron, all of it was created in stellar furnaces and scattered into space by supernova explosions. Those atoms drifted through the emptiness of interstellar space for millions of years, carried by the expansion of the universe, eventually collecting into the cloud of gas and dust that became our solar system. From that cloud, the sun formed, the planets formed, Earth formed. Over billions of years, chemistry became biology, simple life became complex life, and eventually, you are the end product of nearly 14 billion years of cosmic evolution. You are made of atoms that have traveled across light years of emptiness to find each other in this particular arrangement, in this particular moment, reading or hearing these particular words. You are star stuff, as Carl Sagan famously said, but you're also made of the void between the stars. The empty space that allowed those atoms to travel to you is part of your history. The nothing between things is what allowed things to connect, to combine, to become something new. You are matter and void, something and nothing intertwined. Every time you take a breath, you're pulling in atoms that have journeyed through emptiness. Every time you eat, you're incorporating matter that has passed through the cosmic void. You are a meeting place for atoms that have traveled across light years of nothing to find each other. You are a temporary gathering of matter, held together for a brief moment in cosmic time, aware of itself and its surroundings. There's something profound about this. The universe is mostly empty, and yet from that emptiness, consciousness has emerged. Nothing has given rise to everything that matters to us. Love exists in a universe that is fundamentally void. Beauty exists in a universe that is overwhelmingly nothing. Curiosity, wonder, joy, compassion, all of it has emerged from emptiness. Perhaps that's the deepest truth about empty space. It's not the opposite of something. It's the condition that makes something possible. It's not absence, it's potential. The void is pregnant with possibility. Everything that has ever happened or will ever happen unfolds within the embrace of nothing. When you look up at the night sky and see the stars scattered across the darkness, you're seeing this truth expressed at cosmic scales. The bright points of light, the distant galaxies, the nebulae where new stars are being born, they're beautiful, but they exist within a vast ocean of emptiness, and that ocean is part of their beauty. The darkness frames the light, the silence makes the music meaningful, the nothing holds the something and gives it context. The quantum vacuum, seething with virtual particles even in the emptiest space, reminds us that even the purest nothing is full of activity. The universe at its most basic level is not static. It's dynamic, creative, constantly generating and absorbing possibilities. The nothing of empty space is always doing something, even when no ordinary matter is present. We began this journey asking about empty space. We wanted to understand why nothing seems to be everywhere. Now we have our answer. Nothing is everywhere because nothing is necessary. The universe requires emptiness to function. Space, time, matter, energy, chemistry, biology, consciousness, all of it depends on the void. Without the emptiness inside atoms, there would be no chemistry, no complexity, no life. Without the emptiness between objects, nothing could move or change. Without the emptiness between stars and galaxies, there would be no structure, no evolution, no time for interesting things to happen. Empty space is not a failure of the universe to fill itself with matter. It's a feature, not a bug. It's the medium in which existence unfolds. It's the stage on which the drama of the cosmos plays out. It's the canvas that makes the painting possible. The next time you feel small or insignificant, remember that you're made of the same stuff as stars, and that stuff is mostly nothing. You are the universe's way of contemplating its own emptiness. You are organized void, given the gift of awareness. You are almost nothing that has become something, emptiness that has learned to think. That's not a cause for despair. That's a cause for wonder. That's the most remarkable thing in the universe. The nothing that fills the cosmos is your home. It's where you came from. It's where your atoms traveled through before they became you. It's where everything will eventually return. And in between, in this brief, precious moment in cosmic time, you get to experience it. You get to wonder about it. You get to feel awe at the vastness and meaning, at the beauty, from almost perfect emptiness. Something as complex and beautiful as consciousness has emerged. From nothing, everything that matters has come, and you are part of that emergence. You are the void contemplating itself. You are the nothing that became something. Empty space is everywhere. Nothing is the default state of the universe, but that nothing has given rise to everything worth caring about. The void has produced minds that can recognize its own vastness. And that, perhaps, is the most remarkable thing of all. We've journeyed tonight from atoms to galaxies, from quantum vacuum to cosmic voids. We've seen that the universe is emptier than most people realize. We've learned that empty space isn't really empty but seethes with quantum activity. And we've discovered that without all that nothing, there would be no something. The nothing of empty space isn't lonely or bleak. It's the canvas on which complexity paints its portrait. It's the silence that makes the music meaningful. It's the darkness that reveals the light. It's the potential from which all actuality springs. Thank you for taking this journey with me. If you found value in this exploration, please consider liking this video and subscribing to the channel. Your support helps me continue making these deep dives into the wonders of the cosmos. And remember, The next time you pick up a coffee cup or look up at the stars, you're experiencing something miraculous. Your matter contemplating matter. Your organized emptiness wondering about the void. In a universe made almost entirely of nothing, you are something. And that something is precious beyond measure. The emptiness around you isn't empty. It's full of possibility. It's full of quantum activity. It's full of the conditions that made your existence possible. Nothing, properly understood, is actually everywhere. And that might be the most beautiful truth the universe has to offer. Sleep well tonight knowing that the void surrounds you, supports you, and made you possible. The nothing that fills the cosmos is not your enemy, it's your origin. It's the womb from which complexity was born. And in understanding that, you've glimpsed something profound about the nature of existence itself. The universe is mostly nothing, but from that nothing, you emerged. And for a brief, shining moment in cosmic time, you get to be something. You get to think and feel and wonder and love. That's not nothing. That's everything. Good night.